In the silent, unending theater of the cosmos, new actors constantly emerge from the wings, their paths intersecting with the grand familiar dance of planets. We are accustomed to the clockwork precision of our solar system, a delicate gravitational ballet that is played out for eons, shaping our very existence. But what happens when an unexpected visitor arrives? A traveler from the interstellar void, carrying with it the mysteries of a realm far beyond our own sun. This is the story of such a traveler, a celestial object designated 3I/Atlas, an enigmatic body that has recently captured the attention of astronomers worldwide. Its journey began in darkness, in the cold, sparse expanse between the stars, a place where our sun is just another point of distant, anonymous light. After a voyage of unimaginable duration, it has now crossed into our cosmic neighborhood, its presence detected by the vigilant electronic eyes of our telescopes. The initial observations raised immediate and profound questions, not just about the object itself, but about its ultimate destination within our carefully balanced system. A trajectory was calculated, a faint line drawn through the vast emptiness of space, and one particular point on that line sparked intense scientific curiosity. That point was Mars, the red planet, our neighbor in the cosmos and a world that holds a special place in our quest for understanding. The central question became unavoidable. Is this interstellar wanderer, 3I Atlas, on a collision course or a close approach path with the planet Mars? To answer this, we must first understand the messenger itself. What exactly is this object that has journeyed so far to grace our solar system? Discovered by the Atlas Survey, a planetary defense system designed to find hazardous near-Earth objects, its nature was not immediately clear from the initial data. The I in its designation stands for interstellar, marking it as only the third such object ever confirmed to have originated from outside our solar system. Unlike the planets and asteroids born from our own sun's protoplanetary disk, 3I/Atlas is an alien, a true outsider to our cosmic family. Its composition, its structure, and its history are fundamentally different, offering a rare and precious sample of another star's planetary building blocks. Scientists around the globe turned their most powerful instruments toward this faint speck of light, eager to decode the secrets locked within its ancient ice. They sought to understand its speed and its angle of approach, key variables that confirm its exotic, interstellar origins beyond any shadow of a doubt. A hyperbolic trajectory, an open-ended path not bound to our sun's gravity, is the telltale signature of an object merely passing through our system. This visitor is not here to stay, it is on a grand tour, and our solar system is but one fleeting stop on its unending cosmic pilgrimage. With its interstellar identity confirmed, the focus sharpened intensely on its predicted path, especially its potential encounter with the fourth planet from the Sun. The initial calculations were complex, filled with uncertainties. The object was far away, and its faintness made precise measurements a significant astronomical challenge. Early orbital plots showed a path that would bring it tantalizingly close to the orbit of Mars, a prospect that ignited both excitement and concern. The implications of such an encounter are vast, ranging from a spectacular observational opportunity to a potential, though highly improbable, impact event. To refine the prediction, scientists needed more data. Every night, telescopes tracked 3I/Atlas, adding new data points to the orbital models. They watched for subtle changes in its brightness and for the development of a coma or tail, the classic signs of a comet's ice vaporizing. This outgassing, the release of gas and dust, can act like a tiny, unpredictable rocket engine, subtly altering the object's path through the solar system. Understanding this non-gravitational force is absolutely critical for making accurate long-term predictions about where a comet is truly heading in space. So, what have the latest, most precise observations revealed? What did scientists just find out about this interstellar comet's fateful rendezvous? The global astronomical community has now processed weeks of new tracking data, running it through the world's most sophisticated orbital simulation software. The updated trajectory is now known with a much higher degree of certainty, narrowing the cone of uncertainty that once shrouded its future path. This brings us to the heart of the matter, to the new scientific consensus that has emerged regarding the future of 3I/Atlas and its proximity to Mars. The journey to this conclusion is a testament to the power of the scientific method, a process of continuous observation, refinement, and collaboration. It involves separating the signal from the noise, accounting for every tiny perturbation, from the gravitational pull of Jupiter to the gentle push of sunlight itself. We are peeling back the layers of cosmic mechanics to reveal a future that was, only a short time ago, completely unknown and uncertain. The story is not just about a rock in space. It is about our ability to predict the future, to chart the course of celestial wanderers. Before we reveal the final verdict on the comet's path, it is crucial to appreciate the scale we are dealing with in our vast solar system. The distances between planets are almost incomprehensibly large, and orbital paths that appear close on a diagram can be millions of kilometers apart. The target of Mars is infinitesimally small in the grand arena of the inner solar system, making a direct impact a statistically remote possibility. But a close approach is a different matter entirely, presenting a unique chance for our Martian orbiters and rovers to study an interstellar object up close. Imagine one of our probes on the surface of Mars, turning its cameras to the night sky to capture an image of an object from another star system. This potential for discovery is what drives the urgency and the excitement behind tracking objects like 3IATLAS with such meticulous precision. The data from such an encounter would be a scientific treasure trove, offering insights into the chemistry and formation of planetary systems beyond our own. We would gain a direct window into the composition of a world that orbits a completely different star, hundreds or thousands of light years away. This is the context we must hold as we explore the final, refined orbital data that has recently been published by the world's leading astronomers. The story has now moved from one of speculation and broad possibilities to one of high-precision celestial mechanics and predictable cosmic encounters. What we have learned is a definitive chapter in the ongoing saga of our solar system's interaction with the wider galactic neighborhood. The universe has sent us a messenger, and our scientific instruments have allowed us to read the message it carries in its trajectory. So let us now embark on the deeper voyage, exploring the precise details of what scientists have uncovered about the path of 3I Atlas. We will dissect the data, visualize the encounter, and understand what this event truly means for our exploration of Mars and the cosmos. Prepare to witness the resolution of this cosmic question, a conclusion born from the tireless pursuit of knowledge and our gaze upon the stars. The definitive answer, gleaned from the relentless accumulation of photons and data points from observatories across Earth, is now clear. The latest orbital models, refined to an unprecedented degree of accuracy, show that the interstellar comet 3IATLAS will not impact the planet Mars. The red planet is, and will remain, safe from this particular cosmic wanderer. However, this conclusion does not diminish the significance of the event. In fact, it transitions the narrative from one of potential hazard to one of immense scientific opportunity. The updated trajectory reveals that the comet will pass Mars at a distance that is, on a cosmic scale, remarkably close, offering us a front-row seat to a visitor from another star system. The new data projects a closest approach of approximately 1.6 million kilometers from Mars. While this sounds like an enormous distance, in the vast emptiness of the solar system it is considered a significant near miss. This proximity is a rare gift, a chance to study an alien object with the sophisticated array of instruments we already have in orbit around and on the surface of Mars. To comprehend this encounter, we must visualize the celestial mechanics at play. Imagine the flat plane of the solar system, with the planets moving on their established orbital highways. The interstellar comet is not abiding by these rules. It is cutting through this plane at a steep, unusual angle, a testament to its foreign origins. The initial uncertainty in its path stemmed from a fundamental cometary process known as outgassing. As 3IATLAS approached our Sun, the star's radiation began to heat its icy nucleus, causing frozen gases like water, carbon monoxide, and carbon dioxide to sublimate directly into space, creating a glowing shroud called a coma. This process is not uniform. Jets of gas and dust can erupt from active regions on the comet's surface, acting like unpredictable miniature thrusters. These non-gravitational forces, however minuscule, can nudge the comet off its purely gravity-defined path, and over vast distances, these tiny nudges can result in trajectory changes of millions of kilometers. Early observations had not gathered enough information to accurately model the strength and direction of these jets. This created a cone of uncertainty in the comet's future position, a cone that in the early days did happen to intersect with the position of Mars, leading to the initial scientific alert and intense follow-up observation campaigns. But as astronomers continued to track 3IATLAS day after day, they were able to observe how its path was deviating from a purely gravitational orbit. By carefully measuring this deviation, they could effectively calculate the net effect of the outgassing, creating a much more sophisticated and accurate model of its future movements. This is the triumph of the scientific process. It is a story of reducing uncertainty through persistent observation. The cone of possibilities narrowed, and the projected path of 3IATLAS shifted definitively away from the physical location of Mars, resolving the question with a high degree of statistical confidence. Now, the focus of the global science community has pivoted. Teams managing the missions at Mars are drawing up plans to repurpose their instruments. They are shifting their gaze from the geology of the Martian surface to the deep sky, preparing for the fleeting passage of this interstellar guest. Consider the Mars Reconnaissance Orbiter, a sophisticated satellite equipped with powerful cameras and spectrometers. While designed to map the Martian surface in exquisite detail, its instruments can be reoriented to look at the comet as it passes, analyzing the specific wavelengths of light reflecting off its coma and tail. This spectral analysis is like a cosmic fingerprint. It can reveal the chemical composition of the dust and gas being shed by the comet. Are the ratios of certain elements and molecules the same as in our comets? Or do they betray a different chemical history, forged in the crucible of another, distant star? We could potentially measure the ratio of deuterium to hydrogen in the water ice vaporizing from its nucleus. This ratio is a key clue to where in a protoplanetary disk an object formed, telling us if the building blocks of planets around other stars share a common chemical heritage with our own. Then there are the rovers on the surface, like Perseverance and Curiosity. While their primary mission is geology, they are also equipped with advanced weather and atmospheric sensors, and most importantly, high-resolution cameras that can be pointed toward the Martian sky. An image of an interstellar comet taken from the surface of another planet would be more than just a breathtaking photograph. It would be a landmark achievement in human exploration, a testament to our presence as a multiplanetary species capable of bearing witness to cosmic events from different worlds. The thin Martian atmosphere, largely free of the light pollution and distortion that plagues Earth-based observers, could offer an exceptionally clear view. The rovers could track the comet's movement against the backdrop of Martian stars, providing yet more data points to refine our understanding of its path. Orbiters like MAVEN, which is designed to study the Martian atmosphere, could even attempt to detect if any material from the comet's tail interacts with the planet's tenuous outer atmospheric layers. This is a long shot, but the possibility of capturing and analyzing alien material directly is incredibly tantalizing. The close pass of 3I/Atlas is therefore a dress rehearsal for future encounters. It is a critical exercise for our planetary defense coordination networks, allowing them to hone their tracking and prediction capabilities. Each interstellar object that passes through teaches us more about how to respond if one is ever found on a direct collision course with Earth. This event underscores a profound shift in our understanding of the cosmos. For centuries, we viewed our solar system as a largely isolated island in the vast ocean of the galaxy. We now know that the channels between these stellar islands are far more active than we ever imagined, with messengers constantly making the crossing. These interstellar objects are time capsules. They have journeyed for millions, perhaps hundreds of millions of years, through the deep, cold void. They are pristine samples of the raw materials that were present in another solar system when it was first forming, carrying an unaltered record of its primordial chemistry. By studying 3I/Atlas, we are not just looking at a comet. We are looking back in time and across immense distances to the birth of a planetary system that is not our own. We are performing a kind of remote, interstellar archaeology, piecing together the story of another world's creation. The information we gather will feed into our models of planet formation, helping us understand if the processes that created Earth are common or rare throughout the galaxy. Every piece of data, every spectral line is a new brushstroke in our grand portrait of the cosmos, and our place within it. As the date of the comet's closest approach to Mars draws nearer, a coordinated, multinational observation campaign will swing into full effect. Telescopes on Earth will join with our robotic emissaries at Mars, all focused on this single, fleeting point of light, this ambassador from a distant sun. The encounter itself will be a slow, silent, and graceful affair. Over a period of several days, the comet will brighten in the Martian sky, trace its path across the constellations, and then slowly fade as it continues its journey back out into the unending darkness of interstellar space, never to return. Its passage is a reminder of the dynamic and interconnected nature of the galaxy. It highlights that the space between stars is not empty, but is instead populated by countless such wanderers, remnants of planetary formation ejected from their home systems by gravitational interactions long ago. The story of 3 IATLAS and Mars is therefore not one of impending doom, but one of profound discovery and connection. It connects our present exploration of Mars with the ancient history of a distant star system. It connects our most advanced technology with the fundamental questions of our cosmic origins. It represents a unique moment in human history, where we are no longer just passive observers of the cosmos from a single vantage point. We have established an outpost on another world, and that outpost is now becoming our forward observation post for the wider galaxy. The trajectory data tells us where the comet will be, but the scientific data it will provide is what will truly shape its legacy. This is a story that has shifted from the realm of orbital mechanics to the realm of astrophysics and astrochemistry, the very science of what the universe is made of. The question of what if it hit has been replaced by the far more compelling question of what can it teach us? This is the essence of scientific inquiry, turning a perceived threat into a source of knowledge and a moment of uncertainty into an opportunity for profound wonder. As we prepare to witness this silent, distant rendezvous, we are reminded of the clockwork elegance of the universe. The laws of gravity that guided this object across unimaginable distances are the same laws that allow us to predict its path with such stunning accuracy. The precise calculations have given us reassurance, but they have also given us a gift, a specific time and place where we can point our instruments to intercept a message in a bottle that has been floating on the cosmic ocean for longer than humanity has existed. The non-gravitational forces that once clouded our view are now the very subject of intense study. How much water is it losing every second? What is the ratio of dust to gas? The answers will help us build better models for all comets, both those from our home system and those that visit from afar. This entire event is a powerful demonstration of our growing capabilities as cosmic citizens. We detected a small, faint object from the void. We identified its exotic origins. We calculated its path, grappled with its uncertainties, and ultimately predicted its future with life-affirming precision. The focus on Mars is particularly poignant. As we plan for a future human presence on the red planet, we must understand the environment it exists in. This includes not just its own geology and atmosphere, but its vulnerability to and interaction with the wider solar system and even the galaxy. This comet's journey and our study of it is part of that crucial reconnaissance. Every piece of information makes our future expansion into the solar system safer and more informed. We are not just exploring space, we are learning how to live in it, and that includes understanding all of its inhabitants. The color of the comet's dust, the signature of its carbon-based molecules, the nature of its frozen water, all of this tells a story. It speaks to the universal nature of chemistry and physics, suggesting that the very ingredients that led to life on Earth may be common building blocks throughout the galaxy. The trajectory may miss Mars, but the scientific implications will hit home for astronomers for years to come. The datasets collected during this brief flyby will be analyzed and reanalyzed, forming the basis of scientific papers and doctoral theses that will push the boundaries of our knowledge. It is a moment of deep, contemplative calm. The initial alarm has subsided, replaced by the quiet, focused excitement of impending discovery. The universe has presented us with a puzzle, and our global scientific community has risen to the challenge of solving it with rigor and elegance. The final trajectory is a beautiful line drawn through space-time, a testament to the predictive power of science. It is a path that brings a piece of another world into our backyard, allowing us to study it without ever having to leave our own solar system. This is the modern age of exploration. It is not always about sending ships to distant lands. Sometimes, it is about having the intelligence and the technology ready to analyze the distant lands when they, by chance, drift past our shores or the shores of our neighboring worlds. So, as 3IATLAS continues its silent, inexorable journey toward the inner solar system, our robotic eyes on and around Mars are preparing to turn outwards. They will witness a spectacle that no human has ever seen directly, a visitor from another star, viewed from the surface of another planet. The data that will be streamed back across millions of kilometers of empty space will contain the comet's secrets. It will be a transmission not just of numbers and images, but of a deeper understanding of our connection to the grand galactic story that is constantly unfolding all around us. The Martian night sky, for a brief period, will host a new, temporary star, a faint smudge of light carrying the condensed history of a solar system we will never see. And our rovers, our lonely robotic explorers, will be there to record its passage for all of us. This entire chapter in Cosmic Discovery serves to humble and inspire us. It shows us the vastness of space, the precision of physics, and our own remarkable ability to reach out with our intellect and our instruments to touch the unknown and bring its secrets into the light of understanding. The story of 3I/Atlas is not about a collision, it is about a connection. It is about the profound realization that our solar system is not a closed system, but an open port on the interstellar ocean, and we are just beginning to learn about the other vessels that sail upon it. The final verdict is in: Mars is safe, but the scientific adventure is only just beginning. The close approach of this interstellar comet promises to be one of the most significant astronomical observation campaigns of recent years, all centered on our planetary neighbor. We will look at the light from this object, filtered through our instruments at Mars, and decode a message that has been traveling for millennia. It is a message about the universality of matter and the shared origins of all star systems, including our very own. The comet serves as a celestial bridge connecting our world and our exploration of Mars to the wider galaxy. It reminds us that even as we focus on the worlds next door, we are intrinsically part of a much larger, much older, and much more mysterious cosmic narrative. Let us now delve even deeper into the specifics of this planned observation. What exactly are we looking for? And what technologies will we employ in this unique, interplanetary scientific endeavor? The answers reveal the cutting edge of modern astrophysics and planetary science. The silent ballet between the interstellar wanderer and the red planet is about to begin. And we, through our robotic proxies, will be there to witness it, ready to capture the knowledge it offers before it vanishes back into the profound and silent darkness from which it came. The primary observation platform for this interstellar encounter will be the fleet of robotic orbiters currently circling Mars. These sophisticated probes, our sentinels at the red planet, will pivot from their geological surveys to become astronomical observatories. Their suite of advanced instruments is uniquely positioned to capture data that is impossible to obtain from Earth due to the filtering effects of our own dense atmosphere. At the forefront of this effort is the Mars Reconnaissance Orbiter's CRISM instrument, the compact reconnaissance imaging spectrometer for Mars. By analyzing the infrared light reflected from the comet's coma, CRISM can identify the spectral signatures of various minerals and frozen gases, providing a detailed inventory of the raw materials that constitute this alien object's nucleus. Simultaneously, the HiRIC camera, the most powerful telescopic camera ever sent to another planet, will attempt to resolve the comet's inner coma and perhaps even its nucleus. While the object will still be just a point of light, HiRIC can precisely measure its brightness and look for any outbursts or fragmentation events, offering clues about the comet's structural integrity and rotational period. Other orbiters, like Europe's Trace Gas Orbiter, will employ their own spectrometers, which are exquisitely tuned to detect trace amounts of specific gases. They will be searching for the chemical fingerprints of molecules like methane and water vapor in the comet's tail, trying to determine if their isotopic ratios differ from those found in the comets of our own solar system. This orbital campaign is a delicate dance of resource management. Mission controllers on Earth will carefully calculate the optimal times to reorient the spacecraft, balancing the precious fuel expenditure against the immense scientific value of each observation. Every kilobyte of data will be a hard-won prize streamed across the interplanetary void. The second front of this observational campaign will unfold on the planet's surface. Here, the mission is more challenging. The rovers were not designed as astronomical platforms, but their capabilities offer a unique, ground-level perspective. Their cameras, intended for geology, will be turned to the heavens, transforming them into robotic astronomers. The Mastcam-Z camera system on the Perseverance rover, with its powerful zoom capabilities, will attempt to image the comet. While it won't see much detail, the sequence of images will create a time-lapse movie of the interstellar visitor moving across the thin, alien sky, providing a powerful and iconic record of the event. Furthermore, the rovers are equipped with atmospheric science instruments. As the comet passes, these sensors will be on high alert for any hint of material from its tail interacting with the upper Martian atmosphere. The detection of even a few stray molecules of interstellar dust would be a groundbreaking discovery, a direct sampling of another solar system. Imaging the comet from the Martian surface presents a unique set of challenges for engineers. The object will be faint, and the cameras will need to use long exposures. This requires the rover to remain perfectly still, a task complicated by the planet's winds and the thermal changes that cause the rover's metal body to expand and contract. This coordinated effort between orbit and surface creates a complete three-dimensional view of the encounter. The orbiters provide the detailed spectroscopic analysis from above, while the rovers provide the visual context and potential for atmospheric detection from below. Together, they form a comprehensive interplanetary observatory. The core of this entire scientific endeavor is the science of light itself, a field known as spectroscopy. Every element and molecule absorbs and emits light at specific, unique wavelengths. By splitting the faint light from the comet into its constituent colors, like a rainbow, astronomers can read its chemical barcode. Scientists will be looking for the telltale signatures of water ice, a fundamental ingredient for life as we know it. Confirming its presence would support the theory that water is a common component in planetary systems throughout the galaxy, delivered by comets and asteroids during their formation. They will also search for complex organic molecules, the carbon-based compounds that are the building blocks of life. Finding these molecules in an interstellar object would have profound implications, suggesting that the raw ingredients for biology are not unique to our solar system but are instead distributed across the stars. The ratio of different types of elements, known as isotopes, is another critical piece of the puzzle. For example, the ratio of nitrogen-15 to nitrogen-14 can tell scientists about the temperature and chemical environment where the comet originally formed, providing a direct comparison to the birth conditions of our own sun. This decoding of light is a meticulous process. The signal from the comet is incredibly faint, buried in the background noise of the cosmos. It requires sophisticated computer algorithms to filter and amplify the signal, slowly revealing the chemical secrets locked within the ancient ice of 3I/Atlas. The observational strategy extends beyond what our eyes can see, venturing into the invisible realms of the electromagnetic spectrum. Infrared observations are particularly crucial because they can reveal information about the comet's temperature and the composition of the dust grains it is shedding into space. Dust warmed by the sun glows in infrared light. By analyzing this glow, scientists can determine the size, shape, and mineralogy of the dust particles. Are they fluffy, porous aggregates, or are they solid, crystalline grains? This tells us about the physical processes in the protoplanetary disk where it formed. Conversely, ultraviolet observations reveal the processes occurring in the coldest, most energetic parts of the comet's coma. Certain gases, when broken apart by the sun's harsh ultraviolet radiation, fluoresce brightly at specific UV wavelengths, providing the clearest view of the composition of the vaporizing ices. This multi-wavelength approach provides a more complete picture of the object. Visible light shows us the reflected sunlight from the dust, infrared shows us the heat radiated by that dust, and ultraviolet shows us the composition of the gas. Each piece is essential to building a comprehensive model of this interstellar visitor. By combining all of this data, scientists can create a holistic profile of 3I/Atlas. They can estimate its size, its outgassing rate, its chemical makeup, and its physical structure, comparing these properties to the hundreds of comets from our own solar system that we have studied in detail. While the Mars-based assets provide the close-up view, the entire campaign is supported by a global network of telescopes on Earth. These ground-based observatories have the advantage of massive mirrors and highly specialized instruments that are too large to send to Mars, providing crucial supporting data. Large survey telescopes will continue to track the comet's position with extreme precision, refining its orbit down to the kilometer level. This constant stream of astrometric data is the foundation upon which the entire Mars observation campaign is built, ensuring the probes are looking in the right place at the right time. Giant radio telescopes may also be used to listen for specific radio frequencies emitted by certain molecules in the comet's coma. This technique can detect gases that are invisible to optical and infrared telescopes, adding yet another layer to the complex chemical analysis being performed. Furthermore, space telescopes in orbit around the Earth, like the Hubble and James Webb successors, will contribute their own unique capabilities. Their position above the distorting effects of the atmosphere allows them to perform incredibly sensitive spectroscopic observations over long periods, complementing the snapshots taken by the Mars orbiters. This creates a truly interplanetary and collaborative scientific effort. Data from Earth-based telescopes, Earth-orbiting telescopes, Mars-orbiting probes, and Mars surface rovers will all be pooled together. No single observation tells the whole story. The truth lies in the synthesis of all this information. The time difference between Earth and Mars also creates a unique opportunity. Because of the vast distance, the two planets see the comet from slightly different angles. This parallax effect can be used to triangulate the comet's position and dusttail with extreme accuracy, providing a 3D perspective. This vast, coordinated network of instruments represents humanity's collective intellect and curiosity. It is a planetary-scale system designed to investigate a visitor that is merely planetary-sized, a remarkable focusing of our global resources on a single profound scientific question. The legacy of this event will not just be the data collected, but also the methods developed to collect it. The techniques honed in tracking and coordinating observations of 3IATLAS will become the standard procedure for all future interstellar object encounters, making us better prepared for the next visitor. Ultimately, this campaign seeks to answer a fundamental question. Are we typical? Is the architecture and chemistry of our solar system a common outcome of star formation? Or is it a rare exception? Interstellar objects like 3IATLAS are the only samples we have to begin answering this query. Each photon captured, whether by a rover's camera on Mars or a giant mirror on a mountaintop on Earth, is a small piece of the answer. It is a fragment of a message from a distant star system, a message that we are now, for the first time, technologically capable of reading. As the comet gets closer, the activity on its surface will likely increase. The sun's growing influence will cause more and more of its ancient ices to vaporize, potentially leading to unpredictable outbursts of gas and dust that will make it brighten considerably, offering an even better target for our instruments. Scientists will be watching for these outbursts closely. They are significant because they eject material from deep within the comet's nucleus, offering a glimpse of the most pristine, unaltered material that has been shielded from the ravages of cosmic radiation for billions of years. The orientation of the comet's tail will also be a key area of study. The dust tail, pushed by the gentle pressure of sunlight, will curve gracefully along the comet's orbit. The ion tail, composed of charged gas, will be pushed straight away from the sun by the solar wind, creating a cosmic signpost. Observing how these two tails interact with the tenuous Martian environment will provide invaluable data. It will test our models of solar wind physics and how planetary magnetospheres, or the lack thereof in Mars' case, deflect these streams of incoming solar and cometary particles. This entire event is a grand experiment in celestial mechanics and astrochemistry, laid out for us on a planetary scale. The comet is the subject, Mars is the laboratory, and our robotic probes and rovers are the tireless research assistants conducting the experiment on our behalf. The final results will not be known immediately. The vast amounts of data collected will take months, even years, to be fully processed, analyzed, and understood. The passage of 3I/Atlas is a fleeting event, but its scientific impact will resonate for a generation. From the initial detection as a faint, unassuming dot to the alarming possibility of a Martian encounter, And now to this unprecedented scientific opportunity. The story of 3I Cantless is a perfect microcosm of the scientific process, a journey from uncertainty to knowledge. The object itself is indifferent to our gaze. It is following the simple, elegant laws of physics that govern all motion in the cosmos. It is on a path dictated by gravity and solar radiation, a path that, by pure chance, is bringing it within the sphere of human scientific inquiry. Our ability to anticipate this path and prepare for it is a profound statement about our place in the universe. We are no longer limited to simply wondering at the lights in the sky. We can now engage with them, interrogate them, and learn their stories. The knowledge we gain will be woven into the grand tapestry of our cosmic understanding. It will inform our search for habitable worlds, our models of planetary defense, and our philosophical conception of our own origins, connecting us more deeply to the universe we inhabit. The silent approach continues. Day by day, 3I draws closer, its faint glow a beacon of new knowledge. On Earth and at Mars, the final preparations for the observational sequence are underway, a testament to our relentless drive to explore and to understand. The comet's trajectory is now known with such precision that mission scientists can pinpoint the exact square kilometers of the Martian surface from which the best views will be possible, positioning our rovers as if setting up a camera for a once-in-a-lifetime celestial photograph. This moment is the culmination of decades of investment in planetary science. The infrastructure we have painstakingly placed on and around Mars is now being leveraged for a bonus science objective, one that was never envisioned when the missions were first designed. The data will ultimately be made public, available to any scientist around the world who wishes to study it. This collaborative, open approach to science ensures that the maximum amount of knowledge is extracted from this rare cosmic event, benefiting all of humanity. We stand on the precipice of a remarkable new chapter in the exploration of our solar system. We are about to conduct the first ever close-range study of an interstellar object using assets stationed on another world, a sentence that would have been pure science fiction only a generation ago. The story is no longer about a potential threat, but about a guaranteed reward, the reward of pure knowledge. It is the prize that has driven explorers and scientists throughout history. The simple, profound desire to see what lies beyond the next hill, or in this case, the next star system. As the comet brightens, so too does our understanding. Each observation will strip away a layer of mystery, replacing it with the hard, beautiful clarity of scientific fact. We are witnessing the conversion of the unknown into the known, live on an interplanetary stage. The journey of 3I through our solar system is a fleeting cosmic moment, but for us, it is a defining one. It represents a maturation of our species, ability to not just inhabit our corner of the cosmos, but to actively engage with it in a meaningful, scientific way. The stage is set, the instruments are calibrated, the trajectory is confirmed. All that remains is for the cosmic clockwork to proceed, bringing this messenger from afar into the waiting view of our robotic eyes, ready to capture its secrets for posterity. The encounter will be a silent, distant event, but its echoes will be heard in the halls of scientific institutions for years to come. It is a moment of pure exploration, a chance to touch a piece of the galaxy without ever leaving our own cosmic neighborhood. Behind every robotic command and every stream of data, there is a profoundly human story. Teams of scientists and engineers, separated by continents and oceans, are working in unison. They are the unseen choreographers of this cosmic ballet, their collective expertise focused across millions of kilometers of space to guide our probes toward this singular, scientific goal. These individuals spend their careers preparing for moments like this. For them, 3I/Atlas is not just an astronomical curiosity, it is a validation of their life's work. The long nights spent writing code, designing instruments, and planning missions all culminate in these fleeting encounters, where the boundary of human knowledge is tangibly pushed forward. The communication between Earth and Mars is a significant challenge in this endeavor. There is a light time delay of many minutes, meaning commands cannot be issued in real time. The observation sequences must be programmed, uploaded, and automated far in advance, with the human controllers trusting their calculations and the autonomy of their robotic explorers. This process is a testament to our ability to project our intelligence and intention across the solar system. We have built extensions of our senses, placing them on and around another world. We are not just observing the comet from afar. We are, in a very real sense, present at Mars, waiting to witness the flyby. Let us now widen our perspective to understand the origin of such cosmic travelers. Interstellar objects like 3IATLAS are not born in the void. They are exiles from their own star systems. They are the leftovers of planet formation, ejected from their homes during a period of gravitational chaos billions of years ago. In the early life of a star system, thousands of small, icy bodies known as planetesimals jostle for position. As giant planets, akin to our Jupiter, migrate and settle into their final orbits, their immense gravity acts as a cosmic slingshot, flinging many of these smaller bodies out of the system entirely and into the vast expanse of the galaxy. Our galaxy is therefore teeming with these homeless wanderers. For every star, there are likely thousands, if not millions, of such objects drifting silently through the interstellar medium. The space between stars is not empty, but rather a repository for the scattered remnants of countless planetary births across cosmic history. The discovery of 3I/Atlas is therefore not a surprise, but rather a confirmation of what our theories of planet formation have long predicted. We are finally beginning to see the evidence of this galactic diaspora, a constant, slow-motion exchange of material between star systems that has been occurring for eons. Every one of these objects is a unique fossil. Each carries the specific chemical signature of the stellar nebula in which it formed. By studying enough of them, we could begin to map the chemical diversity of our entire galactic neighborhood, understanding the variety of conditions under which planets can form. Before 3I/Atlas, we had confirmed only 2 other such visitors. The first was 1I Oumuamua, a bizarre, highly elongated object that tumbled end over end and showed no cometary activity. Its true nature remains a subject of intense scientific debate, a cosmic enigma that passed too quickly for us to study in detail. The second visitor, 2I/Borisov, was more familiar. It looked and behaved much like the comets from our own solar system, displaying a prominent coma and tail. Its discovery was a landmark, proving that comets, a key ingredient in planetary formation, exist around other stars and are fundamentally similar to our own. 3IATLAS now adds a crucial third data point to this emerging field of interstellar studies. It appears to be a classic comet, much like Borisov, but its close pass by Mars provides a research opportunity that was completely absent with the previous 2 objects. We missed the chance to study the first 2 up close. We will not miss this one. This increasing rate of discovery is no accident. It is the direct result of our improved telescope technology and survey strategies. We are building wider, more sensitive electronic eyes on the sky, such as the upcoming Vera C. Rubin Observatory, which are specifically designed to scan the entire sky every few nights. Once this new generation of observatories comes online, the detection of interstellar objects is predicted to become a common occurrence. Instead of 1 every couple of years, we may begin to find several every single month. This will revolutionize the field, turning interstellar archaeology from a novelty into a systematic science. This influx of new subjects will allow us to perform statistical studies. Are most interstellar objects rocky like Oumuamua, or icy like Borisov and Atlas? Do they come from a particular direction in the galaxy, or is their arrival random? These are the questions that a larger sample size will finally allow us to answer. The passage of these objects raises profound, almost philosophical questions about the interconnectedness of star systems. If the raw building blocks of planets are being exchanged throughout the galaxy, could the building blocks of life itself also be part of this cosmic traffic? This is the core of the panspermia hypothesis, the idea that life could be seeded from one world to another, carried across the interstellar void within the shielded, icy hearts of comets. While still highly speculative, the study of objects like 3IATLAS provides the first ever opportunity to test this concept directly. Finding complex organic molecules, or even more tellingly, amino acids, within the material of 3IATLAS would not prove the existence of alien life. However, It would demonstrate that the fundamental chemical prerequisites for life as we know it are not confined to our solar system, but are instead common galactic currency. The comet, therefore, is more than just a scientific target. It is a vessel of cosmic context. Its journey forces us to see our solar system not as an isolated island, but as a port of call on a vast, interconnected galactic ocean, where matter, and perhaps even potential, is constantly being exchanged. This perspective shift is one of the most significant outcomes of these discoveries. We are part of a galactic ecosystem. The dust from our sun's formation may one day drift into another forming star system, and the object now passing Mars is a tangible piece of such a distant event, delivered to our doorstep. This understanding fosters a sense of both humility and connection. It humbles us by highlighting the vastness of the processes that dwarf our own existence. But it also connects us, suggesting that the story of our origins is intrinsically linked to the stories of countless other stars across the Milky Way. As we move forward, the ultimate goal would be to one day intercept one of these interstellar visitors with a dedicated spacecraft mission. Such a mission would be technologically demanding, requiring a rapid launch and incredible speeds, but the scientific payoff of collecting a direct, physical sample would be immeasurable. The close pass of 3I/Atlas at Mars serves as a crucial dry run for such a future mission concept. It allows us to practice our detection, tracking, and rapid characterization capabilities. The lessons learned from this flyby will directly inform the design of any future intercept mission we might plan. We are in the opening moments of a new era of exploration. For all of human history, we have been limited to studying the contents of our own solar system. We are now, for the very first time, able to reach out and analyze pristine material from entirely different families of planets. The story of 3I/Atlas is a reminder that the universe is not a static, unchanging backdrop. It is a dynamic and evolving place, full of movement and interaction. And we, on our small blue world, are just now developing the senses to perceive this grand, cosmic motion. Each new discovery peels back another layer of the cosmos, revealing a universe that is far more intricate, interconnected, and ultimately more wondrous than we had ever dared to imagine. The journey of this single comet is a small but profound chapter in that ongoing revelation. The knowledge we are about to gain from our Martian outposts will be a testament to foresight, planning, and our unyielding curiosity. It is the result of a species that looks up at the night sky and does not just see points of light, but sees a frontier to be explored and understood. The final approach is a moment of quiet anticipation. The commands have been sent. The instruments are ready. Now, all we can do is wait for the photons from this ancient traveler to complete their journey and strike the detectors of our robotic emissaries, delivering their coded message from across the void. What that message will contain is still unknown, but its importance is not. It will tell us more about our galactic neighbors, and in doing so, it will tell us more about ourselves. Every piece of cosmic knowledge is ultimately a piece of self-knowledge, helping us to define our own place in the grand scheme. As we prepare for this influx of new data, we are also preparing for a new understanding. The universe is about to speak to us through the language of physics and chemistry, using a messenger that has traveled for eons to make its delivery at the orbit of the planet Mars. Let us contemplate the immense journey this object has undertaken. For potentially millions of years, it has moved through the near absolute zero of interstellar space. It has drifted through tenuous clouds of gas and dust, and has been witness to the silent, slow-motion evolution of the galaxy around it. Its surface is likely scarred by the impacts of microscopic interstellar dust and eroded by the constant bath of high-energy cosmic rays. It is a truly ancient artifact, far older in its unaltered state than the surfaces of most objects in our own solar system, which have been subject to the sun's more intense influence. The encounter with our sun is a violent, transformative event for the comet. After an eternity in the deep cold, the sudden warmth is causing its very substance to boil away into space. We are witnessing a brief, spectacular moment of activity in an existence that has otherwise been defined by unimaginable quiescence. This process of sublimation is what allows us to study it. The outgassing creates a massive, tenuous atmosphere, the coma, that is far larger than the nucleus itself, providing a much bigger target for our telescopes and spectrometers to analyze from a safe distance. The true prize, however, remains the solid nucleus locked within this gaseous shroud. Direct observation of the nucleus is exceedingly difficult, as it is likely only a few kilometers in diameter and shrouded in a bright cloud of its own making. Its secrets are well guarded. Yet, the composition of the gas and dust that surrounds it is a direct reflection of the nucleus's composition. By studying the shed material in detail, we can reverse engineer the chemistry of the core, piecing together a portrait of the object's fundamental nature and origins. This remote analysis is a triumph of scientific inference. It is like studying an ancient animal by examining the tracks it leaves behind. We cannot see the nucleus directly, but the trail of gas and dust it leaves in its wake tells us a detailed story of where it came from and what it is made of. The successful characterization of 3IATLAS from Mars will mark a significant milestone in planetary science. It will prove the viability of using our existing planetary exploration infrastructure for bonus, high-impact targets of opportunity, adding a new dimension to their scientific return. This event will no doubt inspire a new generation of scientists and engineers. The captivating story of a visitor from another star, studied by robots on the Red Planet, is the kind of real-world science that sparks the imagination and encourages young minds to pursue careers in science, technology, and exploration. Beyond the hard data, this is the lasting legacy of such cosmic encounters. They serve to reignite our collective sense of wonder. They lift our gaze from our terrestrial concerns and remind us of the vast, intricate, and deeply beautiful universe that we are a small but privileged part of. The story of 3I/Atlas is far from over. Even after it passes Mars and begins its long journey back out into the interstellar void, the data it leaves behind will be the subject of intense study for years. Its brief visit will have a long and lasting impact on our science. As it recedes from the sun, the outgassing will cease, and it will once again become a dormant, inert piece of ice and rock. It will fall silent, carrying with it the faint warmth of our star as it begins another multi-million-year voyage toward another, unknown destination in the galaxy. We, in turn, will be left with the afterglow of discovery. The tables of spectral data, the iconic images from the Martian surface, and the refined orbital models will all be integrated into the grand library of human knowledge, a permanent record of our encounter with this celestial messenger. This new knowledge will refine our understanding of galactic ecology. We will have a better sense of the chemical makeup of our interstellar neighborhood, which informs our theories on everything from the formation of stars to the probability of habitable worlds elsewhere in the cosmos. And we will be better prepared for the next one. The lessons learned in coordinating this multi-platform interplanetary observation campaign will streamline our response for the next interstellar object that graces our solar system with its presence, ensuring an even greater scientific return. The future of this science is incredibly bright. As our detection capabilities grow, we will eventually build a comprehensive catalog of interstellar objects, each with its own unique story. We will move from single case studies to a broad understanding of the interstellar population. We may one day detect an object with enough advance warning to launch a dedicated intercept probe, a mission that could fly alongside the visitor, studying it in exquisite detail for months. This is the ultimate dream of interstellar archaeology, a direct, in situ analysis. For now, we rely on these serendipitous close passes. And the pass of 3IATLAS by Mars is one of the most fortuitous alignments in the history of astronomy. A rare object is passing by the one planet, other than our own, where we have the sophisticated tools ready and waiting to study it. This moment represents a convergence of cosmic chance and human ingenuity. The random walk of a comet through the galaxy has, by chance, intersected with the deliberate expansion of the human scientific sphere of influence, creating a singular opportunity for discovery. The silent red plains of Mars are about to become the front line in our study of the galaxy. Our robotic pioneers sent to explore one world are now poised to give us our best ever glimpse into another, a world that orbits a star we may never know the name of. And so, the moment of closest approach arrives. It is an event marked not by sound or spectacle, but by a silent, precise alignment in the vast, three-dimensional emptiness of space. The interstellar comet 3I/Atlas and the planet Mars reach the point of minimum separation. their paths intersecting in time but separated by a gulf of over 1 million kilometers, just as our models predicted. On the surface of Mars, a rover stands motionless, its camera pointed at a specific, pre-calculated point in the pale pinkish sky. For a few hours, it patiently gathers the faint photons that have traveled for years from a distant star, journeyed for months across our solar system, and now fall upon its electronic sensor, capturing a truly alien vista for human eyes. High above, in the silent vacuum, an orbiter swivels on its gyroscopes, its sensitive spectrometer locking onto the faint, ghostly smudge of the comet's coma. It begins its work, dissecting the light, meticulously recording the spectral fingerprints of the elements and molecules that make up this visitor, writing its chemical history into a stream of digital data. This is the moment of contact, not of a physical impact, but of an intellectual one. Our technology, an extension of our own minds, is making contact with an artifact from another star system. It is a quiet, automated, yet deeply profound achievement unfolding in the cold darkness while its architects wait anxiously, a world away. The data packets begin their long journey home. Traveling at the speed of light, they cross the interplanetary void, carrying the precious, hard-won information. Each bit and byte represents a question being answered, a new piece of the cosmic puzzle falling into its rightful place, transmitted from our robotic senses back to our human consciousness. The encounter is fleeting. As quickly as it arrived, 3IATLAS begins to recede. Its gravitational rendezvous with our inner solar system is temporary. It is a passerby, and its trajectory is now bending ever so slightly, not just from the sun's gravity, but from the minuscule gravitational pull of Mars itself, a final, faint interaction before it departs. Now, the second phase of the scientific endeavor begins: the analysis. On Earth, in data centers and university departments around the globe, scientists receive the information beamed back from Mars. The raw telemetry is processed, calibrated, and transformed into graphs, images, and chemical charts, the language through which the comet will tell its story. The first images from the Martian surface are assembled. They will show a faint, elongated streak of light against the familiar backdrop of the Martian sky. This will become one of the most iconic photographs in the history of exploration, a symbol of our multiplanetary reach and our insatiable curiosity about the universe beyond our cradle. The spectral data will be even more revealing. Scientists will pore over the intricate patterns of absorption and emission lines, comparing the chemical makeup of 3IATLAS to our own comets. Is the ratio of carbon to oxygen different? Is there an unexpected abundance of a certain noble gas? These details hold the clues to its unique origins. This is a story of contrasts. The vast, silent, and ancient journey of a comet is met by the focused, modern, and collaborative effort of human science. The cold, indifferent laws of physics that guide the object's path are understood and leveraged by the warm, passionate curiosity that drives our species to explore. The comet's passage serves as a powerful reminder of cosmic timescales. Its journey has lasted for millions of years, an interval so vast it is almost beyond human comprehension. Our entire observation campaign, from detection to analysis, represents an infinitesimally small fraction of this object's long and lonely existence. As 3IATLAS continues on its outbound trajectory, it will cross the orbits of the outer planets, its interaction with them too distant to be significant. It will slowly fade from the view of even our most powerful telescopes, its brief moment of solar-induced glory ending as it returns to the deep freeze of interstellar space. But it does not leave empty-handed. It carries with it the faint gravitational imprint of its passage through our system, and it leaves us with something far more valuable: a wealth of data, a new chapter in our textbooks, and a profound sense of our own growing capabilities as cosmic explorers. The question posed by our title, "Is 3IATLAS heading towards Mars?" has been answered with a definitive and reassuring no. But in the process of answering it, we have uncovered a far more compelling story. Not one of potential disaster, but one of realized scientific triumph and profound cosmic connection. This entire event has recalibrated our perception of planetary defense. It has demonstrated the effectiveness of our sky survey systems and our ability to rapidly calculate and refine the orbit of a newly discovered object, proving that our methods for identifying genuine threats are robust and reliable. It has also shown us that the solar system is a shooting gallery, but one in which the vast majority of projectiles will miss their targets due to the sheer emptiness of space. Our task is to find the one that will not, and the study of 3IATLAS has made us significantly better at that task. The final analysis of the comet's composition will be a legacy for future generations. When the next interstellar visitor arrives, scientists will have the baseline data from Borisov and Atlas to compare it against, allowing them to build a more complete picture of the chemical diversity of our galactic neighborhood. We are at the very beginning of this new science. We are like early naturalists, collecting the first few exotic specimens from a newly discovered continent. Each one is a treasure, offering tantalizing hints of the vast and unexplored ecosystem that lies just beyond our shores, in the great ocean between the stars. The image of that faint comet in the Martian sky will endure. It will symbolize a moment when humanity used its presence on one world to learn about a visitor from another. It is a quiet but powerful declaration that we are no longer bound to a single planetary perspective in our quest for knowledge. This story instills a sense of contemplative calm. The universe, in its immense scale and complexity, is not chaotic but is governed by knowable laws. Our ability to comprehend these laws allows us to predict the future, to avert danger, and to seize fleeting opportunities for incredible discovery. We have learned that our solar system is not an isolated sanctuary, but a dynamic crossroads, constantly visited by travelers from other star systems. This knowledge transforms our view of the galaxy from a static collection of distant lights into a vibrant, interconnected community of stars. The journey of 3IATLAS has also been a journey for us. It has taken us from initial uncertainty to confident prediction, from a single data point to a rich scientific understanding. It is a perfect illustration of the scientific method in action on the grandest possible scale. This encounter has pushed the boundaries of our robotic capabilities. We have tasked our Martian explorers with duties they were never designed for, and they have performed flawlessly. This deepens the bond between human ingenuity on Earth and our robotic extensions across the solar system. The story of this interstellar comet is ultimately a story of light. The light it reflected from our sun, the light that traveled across millions of kilometers to our probes, and the light of understanding that this data now ignites in the minds of scientists and the public alike. So, while the comet itself will soon be gone, its influence will remain. It has provided a crucial test of our systems, a treasure trove of unique data, and a powerful source of inspiration that will fuel our exploration of the cosmos for decades to come. The final data sets will be pieced together, painting the most complete portrait of an interstellar object we have ever had. We will know its chemistry, estimate its size, and understand its behavior, adding a detailed page to our growing encyclopedia of the cosmos. Let us reflect on the profound silence of this entire event. In the vacuum of space, this grand celestial encounter unfolded without a sound. The only voice in this story is our own, the voice of scientific inquiry, of data, and of the narrative we construct to give it meaning. The universe does not offer up its secrets easily. It requires diligence, collaboration, and a relentless pursuit of knowledge. The successful observation of 3I/Atlas is a testament to these human qualities, projected across the vastness of our solar system. In the end, the red planet was not a target, but a partner. It served as the ideal scientific outpost, a stable platform in just the right place at just the right time, allowing us to bear witness to this rare and magnificent celestial event. The feeling that remains is one of deep and abiding wonder. For a brief moment, our cosmic neighborhood was graced by a visitor from an unimaginable distance, and we were ready. We were watching, and we were able to learn its secrets. This event strengthens the case for a robust, multiplanetary robotic presence. The more eyes we have in different parts of the solar system, the greater our chances of observing these rare events, and the more complete our understanding of the cosmic environment will become. The comet is now on a trajectory that will carry it out of our solar system forever. It will never again feel the warmth of our sun. It will return to its eons-long slumber, coasting through the galactic night, a silent vessel that once, briefly, intersected with the light of human knowledge. Our own journey, however, continues. There will be other interstellar objects. 4I, 5I, and beyond are waiting to be discovered. And with each one, our techniques will grow more refined, our questions more sophisticated, and our understanding ever deeper. We have looked upon an artifact from another world not with fear but with curiosity. We have chosen understanding over apprehension. This is perhaps the most important takeaway from the story of 3I Atlas. It is a story of our own maturity as a spacefaring civilization. The universe is a vast and ancient place, and we are a very young species. But events like this demonstrate our remarkable capacity to reach beyond our terrestrial origins and engage with the cosmos in a meaningful and profound way. The data from Mars will continue to be analyzed, and new discoveries will likely emerge from it for years to come. The initial analysis is just the beginning. The deeper secrets of 3I are still hidden within the petabytes of information stored on Earth's computers. This story has a peaceful resolution. There is no collision, no danger, only the quiet acquisition of knowledge. It is a calming reminder that while the universe can be violent, it is also a place of immense, predictable, and breathtaking elegance. Our Martian rovers and orbiters will now return to their primary missions, their gazes turning back down to the canyons, craters, and polar caps of the red planet. But they do so with an expanded legacy, having served as our unexpected ambassadors to the greater galaxy. The comet's brief passage has left an indelible mark not on any planet, but on the landscape of human knowledge. It has connected the exploration of our nearest planetary neighbor with the vast, overarching story of our entire galactic home. We are the universe made conscious, and our study of this distant traveler is a fulfillment of that role: to observe, to measure, to understand, and to weave the silent physical facts of the cosmos into a story of wonder and enlightenment. Let the story of 3I be a source of inspiration. Let it remind us of what is possible when we apply reason, technology, and collaborative effort to the great mysteries that surround us. The frontier of discovery is not a place, but a process. The next time you look up at the night sky, remember that it is not an unchanging canvas. It is a dynamic realm, full of wanderers on epic journeys, and we are, for the first time in history, able to track their paths and learn their tales. The fear of the unknown is replaced by the thrill of the discoverable. This is the gift of science. It transforms cosmic anxieties into grand intellectual adventures, and a faint, passing smudge of light into a profound lesson about our place in the universe. The grand cosmic narrative is always unfolding. New characters emerge from the darkness, play their part on the celestial stage, and then recede. Our privilege is to now have a front row seat, and even, as this story shows, a backstage pass on a neighboring world. The final conclusion is one of sublime reassurance. We live in a universe that is governed by understandable laws, and our growing mastery of those laws allows us to chart a safe and informed course into the future, both on our world and beyond. The encounter is over, but the wonder remains. It settles into a state of contemplative calm, a deep appreciation for the intricate clockwork of the cosmos, and for the patient, persistent human effort required to understand even a small piece of it. From a single, ambiguous point of light to a rich, multifaceted scientific event, the journey of 3I through our awareness has been as remarkable as its journey through our solar system. It is a testament to the power of a single, persistent question. The story concludes, as all great cosmic stories do, with a deeper sense of perspective. Our problems, our triumphs, our entire world are put into the context of a much larger, much older, and endlessly fascinating galactic story in which we all play a part. The interstellar visitor continues its silent, unending voyage back into the void. It leaves behind a quiet solar system and a human species that is just a little bit wiser, a little more capable, and a little more in awe of the grand, silent universe it calls home. And so, we continue to watch the skies, for the story of the cosmos is written in the light of distant stars and silent travelers. We have learned to read its language, and we know that there are always and forever new and wondrous chapters waiting to be discovered.